Hello, everyone, and welcome to the second week of lecture in the Scientific Computing and Python for Data Science unit. This week, we're going to start our discussion with about algorithms. So, in your data course Python directory, there is a notebook called Algorithms, and you'll want to go ahead and click on that. So, thus far, we'll just execute these first two cells. Thus far, we've talked a bit about the basics of programming and how computer programs work. We've discussed some data structures, iteration, and how we might control the flow of a program using conditional if-then statements. We've also talked a little bit about the idea of organizing our code as we write a solution to some problem. And we've even talked a little bit about efficiency of that code. And today we're going to focus on this efficiency question. So for basic programming problems, say things like calculating prime numbers, sorting lists of numbers, finding a number in a list, those sorts of problems are so simple that we can actually write essentially mathematical proofs about them, analyzing how efficiently we can solve those problems. And a lot of those basic tasks end up being building blocks in more complex problems that we want to solve for our specific projects. Generally, whenever we're solving some kind of program on a computer, we're developing an algorithm. An algorithm is the solution to the problem. It's a more abstract idea behind the code. So if I ask you how to sort a list, there's many different ways you could go about it, and you could describe to me in very precise detail how you might do it without ever writing a single line of code. You might say, okay, I take the first element and I compare it to the second element and see which is bigger. If the second element is smaller than the first element, then I swap the two. And then I look at the second element compared to the third element. And I believe, if my memory serves me, you would be describing an algorithm called bubble sort. And it's not very efficient. But notice I didn't have to say anything about code. I just started describing how I would solve the problem. So those instructions, or that approach, is the algorithm. And then I can implement that in code in different ways. So often when we are solving a problem, we're actually doing kind of two separate things. First, we develop an algorithm, some set of instructions or steps that will solve the problem, and then we develop an implementation as we write the code to enact that algorithm. And when we are writing algorithms or problem solving, we'll want to consider several different, or even as we're writing code and implementing an algorithm, we'll want to consider several different questions related to the resources that we use to compute the solution to our problem. So one is time. How many instructions do we need to execute? We have a limited amount of time to solve the problem. Certainly, if we want to accomplish some task, we would like to take it less than our lifetime. So it should take less than 80 or 90 years if you're lucky. For most tasks, we want it to take seconds or milliseconds or microseconds even. So one thing we'll consider as we analyze different algorithms is how does the number of instructions we need to execute grow as the size of our input grows. Another limited resource is memory. How much data do we need to store in memory? Most modern consumer computers have somewhere between 1 and 16 gigabytes of memory, maybe even more. But even though this is quite a lot compared to the amount of memory computers had 10 years ago, or certainly much more than 20 years ago, it's still a limited amount. So we can't store an infinite amount of data in memory. And we may need to consider, how does the amount of memory we use grow as our input grows? And finally, another limited resource in the age of the internet especially is input-output, meaning how much traffic do I need to send in and out of my program in order to accomplish the task. And this traffic could be reads and writes to disk, which are relatively slow, bringing us back to this question about how many instructions do we need to execute and reminding us we have limited time, or how many network reads or writes essentially do I have to make, which not only take time but also take up bandwidth, and many computer systems have limited bandwidth. For instance, I believe at my internet at home, I can't download more than a few megabits per second. So we will, in the remainder of this notebook, consider a few different examples of simple algorithms implemented in a variety of ways, and ask ourselves these questions in order to analyze them. As we talk about these algorithms, we'll be using a particular notation called Big O notation to describe what I said earlier about how does my use of resources grow as the input grows. For example, if for every extra piece of input I need to execute one more instruction, then we would say that my computational complexity grows linearly in the input, or is of order n. And the way that we write order n would be, actually I have to look this up because I forget. If it's just O n like this? No. There we go. So it's this fancy O. It's order n. O stands for order. And that means there is a proportional relationship between the number of instructions I have to run and the size of my input. So for every extra piece of input, I run 3 more instructions, or 4 more instructions. Another possibility is n squared. So here, for instance, you know, I might have to run 3 extra instructions for the first bit of input, and then once I get a second bit of input, I'm running 9 instructions, and then for the third bit of input, I'm running 81 instructions. So actually that's 2 to the n, my mistake, sorry. If I ran 3 instructions for the first piece, then I would be running 3 times 2 squared, so 12 for the second piece, 3 times 3 squared for the third piece, so that's 9 times 3, 27. So we don't really care about the 3 in front. The main thing is that the amount of instructions I have to run grows as n squared. So generally, the kinds of things we're describing is the amount of time that I have to run my program for as a function of n, the input, equals something like a n squared plus b n plus c. As n becomes very large, n squared will be much larger than n, and eventually n much larger than c. For very large values of n squared is bound to be bigger than b times n and c. It will eventually get bigger than these. So the only part of this equation we really care about in terms of how fast does this grow is this n squared. That controls or dominates the behavior of this formula as n gets very big. And that's where these kinds of notations come from, that linear growth or quadratic growth. So we'll be analyzing some of these algorithms using this kind of method where we say, how much more memory do I need for each piece of input, where each the total size of the input is n. So that's a lot of abstract ideas. Let's look at an example. So for our first example, we're going to consider taking the sum of all numbers up to n inclusive of n. So to do that, I could define a function called sumNum, and give it an argument n. The sum is initially equal to 0. And then for each number between 0 and n plus 1, so 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 up to and including n, I will simply add that number to my running sum, and then at the end I will return the total. So sum num2, that would give me 2 plus 1, so 3. Sum num5, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15. So we've just got here 1 plus 2 plus 3 plus 4 plus 5, which is 15. So we can clearly see this works. And now to analyze it, we'll ask ourselves, how many instructions do I need to execute? Well, I essentially need to execute 1 instruction for every number between 0 and n. So as n gets bigger and bigger, I will execute 1 more instruction. So we would say this algorithm is order n. We need to perform about n operations. This n. It's the same n. So as n gets bigger and bigger, we perform proportionally more operations. Linearly proportional more operations. And as I mentioned earlier when I was talking about this kind of mathematical function, even though we have an additional operation here, so we're really talking about like n plus 1, we don't care about this 1 because n will in general be quite a bit larger than 1. So the dominant behavior is this n. The n matters a lot more as it becomes larger and larger than this 1. So we say that, order n includes not only things that are, the amount of time or the amount of instructions grows exactly as n, but it's basically the same as n plus some constant or even some number times n. The thing we care about is just the behavior as a function of n. Now, there is a mathematical trick to performing sums like these. So this is the mathematical formula for this kind of a sum. This big Greek letter sigma just means sum. And if we take the sum of all numbers starting at 1 and going up to capital N, you can prove that this sum is equal to n times n plus 1 divided by 2. So you can derive this formula. There's a Wikipedia page if you're interested. Not this one. Sum of n numbers. Yeah, so if you just Google something like this, you can find this, and whatever you find will probably describe how this is derived. I'm not going to prove it here because this is not a math class. It's a programming class, or at the moment anyway. It's a data science class. So there's this formula. And we could use this formula to write a function that calculates the sum just as before. And we'll do that. So we'll call this sum Gauss because this formula is often attributed to the mathematician Friedrich Gauss. Carl Friedrich Gauss. Anyway, he discovered this formula. And for this way of performing the sum, once you hand me n, I can just return n times n plus 1 divided by 2. And now, if we want to use this, we can see we get the same results as we did before. No problems there. Not 15, 5. So 15 is the result of sum for 5. So exact same answers as we got before, but now analyzing the algorithm, I only have one instruction. And no matter how big n is, I still only execute a single instruction. So compared to earlier, where we had to do n instructions, now we're just doing one. So this algorithm is order 1. Because it does not depend on the size of the input n. And we can go ahead and test that these give the same answer by iterating n from 0 up to 100 and just asserting that the two sums are equal. And remember, I mentioned this in a previous lecture. I don't remember exactly which one. But assertions are special statements where if it's true, nothing happens. But if it's false, we raise an error. So here we're asserting that these two sums are equal. And since nothing happens when we run this cell, it must be the case that the two sums are equal for all these numbers n. So just by looking at these instructions, I can see there's one constant instruction that I execute, no matter how big n is. For this one, since I have a for loop, I'm going to iterate here n times, so I know this algorithm is order n. But I should also check that my analysis, or I can check anyway, that my analysis is correct by timing how long it takes to run this function for a input n compared to how long it takes for this function. And if I increase n, and measure those times again and again as I increase n, I should see that this function takes about the same amount of time no matter how large n is, while this one gets bigger and bigger in a linear fashion. So I'll do that. And to do that, we'll use the time module to time how long it takes to execute the function. And we'll define this fancy function that will do the timing. So we have a list of times, and for each, we're going to run the function several times and compute the average amount of time so that we don't see any spikes in the amount of time it takes to compute just because of transient activity on the server. We're hoping to get a good average time or a sort of representative time by running the function multiple times and averaging it together. So we will find our start time, ts, time start. We'll run the function, and then we will append to our list of times the current time minus the start time. So the elapsed time, the difference in time that is elapsed between when I append the new time to the list and when I started my function. And then I will compute the average just by taking the sum of the times and dividing by the number of times. So I'll do 100 averages for each time point. I'm actually going to reduce this to 10. I think 100 is probably more precise than we need to be, and I want this to run a little bit faster. So I'll do 10 averages for each value of n, and I'm going to look at values of n from 10 to 100,000, taking steps of 5,000. So I'm done doing my timing now. And now I'm just going to plot, and we'll talk about plotting more in a future lecture when we talk about some of the basic data science modules. So I'm not going to get into this plotting code at the moment, but let's just have a look at the plot and see what we can learn. So as the number n, where we're computing this amount of this sum of all the numbers from 1 to n. As n grows, our sum using the Gaussian formula stays the same the entire time. It's just flat. It takes the same amount of time no matter how big n is. The first function we defined, sum num, as n gets bigger and bigger, the amount of time takes longer and longer. And we can see this is basically a straight line. So there's a linear relationship here, which is what we said before. This algorithm takes order n steps. The amount of time it takes to compute grows linearly in the input n. And that's exactly what we see here. So this is just an intro to this idea of analyzing algorithms for how much resources we use to run them. In this example, we focused on the computational complexity. How many instructions did we need to execute? But in future examples, we'll also consider memory needs and input-output, and we'll continue to conduct these kinds of analyses.